Science that's cool, papers so unique.
Welcome back to
Cool Ass Papers that I read this week.
Have you ever wondered what happens to cancer treatment if it doesn't kill the cancer right away? What's up, nerds? I'm Maddie C., PhD in chemical engineering. Every week I break down some of the best papers that I've read in the field of biomedical engineering. This week, the Warren Chan lab out of the University of Toronto examines how nanoparticle-based chemotherapies leave cancer after trying to go in and kill it. It's called The Exit of Nanoparticles from Solid Tumors, and it is easily one of the most important papers when trying to find the mechanisms of how we can kill cancer. But I'm getting ahead of myself. First, we need some important background. Many chemotherapies are made from things called nanoparticles. These are things that are 1,000 times smaller than the thickness of your hair. Nanoparticles are good because they can help to reduce side effects of traditional chemotherapy. Although nanoparticles can work great, only around 1% of the total amount of nanoparticles that are given actually get into cancer. So with all of this in mind, there's a lot of research right now that is looking into how nanoparticles can not only get into cancer, but how they can stay around long enough to kill it. So let's get a little bit more specific. For the last few decades, researchers have assumed that nanoparticles get into and stay into cancer based on this thing called the enhanced permeability and retention effect, aka the EPR effect. And this theory makes two major claims. One, nanoparticles can enter or permeate into cancer tissues from your bloodstream because the blood vessels around cancer have these really big spaces that nanoparticles can easily get into. And two, nanoparticles will stay or be retained in cancer tissue because there's no vessels that can make the nanoparticles exit. In some ways, the EPR effect makes it seem like cancer is a one-way street with a dead end. You can only go in one direction, but since you can't move forwards or backwards, you may as well just stay here for a while and kill some cancer. But recently, more and more researchers are doubting that the EPR effect is even real because it doesn't seem to explain a lot of the phenomena that happens in human cancers. It really only works in mice. In last week's video, I talked about a paper out of the Chan lab that tackled the first claim. So for this week's paper, the same lab tried to tackle the second claim and answer the questions: can nanoparticles leave cancer? And if they do, how? Let's get into it. First thing they needed to do was establish a baseline. They wanted to see if cancer tissues use the same mechanisms that normal tissues do to get rid of nanoparticles and get rid of other waste. These are called lymphatic vessels, which are in charge of bringing waste products out of their original tissues and back into the bloodstream to eventually be redistributed to the correct parts of the body. Researchers have always known that these vessels are located in and around cancer tissues, but it was always assumed that nanoparticles couldn't use them. This diagram is a good representation of what EPRologists thought. On the right side, we see healthy tissue where everything is just doing their thing. The blood vessel is carrying blood, the healthy cells are healthy celling. But what's most important is that the lymphatic vessels, down here in green, are open and available to carry waste. They can do their job. Now the left side shows cancer, which looks very different. The EPR effect thinks that because the cancer is growing so rapidly that it pushes against the lymphatic vessels and closes them shut, thus making it hard to drain the necessary waste. And for years, people thought that this applied to nanoparticles as well. Because the lymphatic vessels were closed, the nanoparticles couldn't leave, thus keeping them around the cancer for a longer time and therefore more chance to kill it. Remember, one-way street, dead end, can't get out. So now it's the Chan's lab's turn to disprove this. After injecting nanoparticles into tumors and then using a high-powered microscope to see where those nanoparticles were going, Warren Chan's group could actually see how many nanoparticles, if any, were getting into these lymphatic vessels. I put two of these images on the screen. The left are lymphatic vessels inside of cancer, and the right is just outside of it. In both images, the black dots you see are nanoparticles. And as you can see, these nanoparticles are definitely in the lymphatic vessels and are likely using them to leave tumors. They could even quantify how many nanoparticles were using these vessels, and over 120 hours, there was between 2 and 4 times as many nanoparticles using these lymphatic vessels compared to the start of the experiment. Turns out that even if cancer is a one-way street, the dead end sign was wrong and you can freely drive on the road until you hit the highway. It's not like you're trapped in the same spot forever. This was a very important first step in disproving that old stinky EPR effect theory, but they felt they needed more evidence, so they took it a step further. This time they injected the nanoparticles into cancer, but then blocked off the lymphatic vessels. They were asking the question, can nanoparticles still leave the tumor if they can't use these lymphatic vessels? Now take a look at this graph, where they're measuring how many nanoparticles are trapped inside of cancer. The green dots represent nanoparticles that were put into cancer without any lymphatic vessels inside. But in white, we see normal cancer. So they do have lymphatic vessels. What we can see is that no matter the size of the nanoparticle, there were significantly more nanoparticles trapped in the cancer when lymphatic vessels were blocked. In other words, it's very strong evidence this is not in fact back to one-way, dead-end, car-broken-down situation, but instead, we hitting the open roads, baby. EPR effect better count their days, because this is yet another figure that suggests that nanoparticles do leave cancer. This might explain why nanoparticle-based chemotherapies don't always work as well as we expect them to, but we'll get to that later. Okay, so we know nanoparticles leave cancer if they're not staying around long enough to kill them. But there's still one very important question to ask. Where are they going? The first place they checked? The heart. They took these incredible images of the entire system, starting from the tumor, through the lymphatic system, and eventually the part of the circulatory system that connects the lymph nodes to the heart. Here's one of those pictures where they labeled the different parts of each pathway. See these big glowing regions? Those are the nanoparticles, which have been labeled with a specific dye to make them glow when under a microscope. More specifically, I've zoomed into the most important part of this image. This is where the lymph node is connected to the heart. Specifically focus on the left subclavian vein and the superior vena cava. And though it's faint, much fainter than the rest of this image, you can see that there's still lots of nanoparticles glowing. But what does this mean? This implies that once the nanoparticles leave the tumor, they eventually get to our heart, which is then pumped throughout the rest of our body. Though this sounds like a bad thing, it could be a really good thing. The authors state that these nanoparticles have the potential to recirculate throughout the body and interact with the tumor in another pass, basically meaning that it gets a second chance to get in and kill the cancer. The suggested mechanism is kind of like a roundabout. You can just keep going around and try new streets until you find the street that you like, which in this case is cancer that you want to kill. Now, you know what? Roads are dumb. This is actually like if you went on a water slide, but instead of being wet and sad at the kiddie pool at the end, it's connected to another water slide that loops you back to the start of the first water slide. And every time you ride the slide, you got a chance to kill cancer, so you just keep going and going and going until that cancer's dead. Whee! So here's a quick summary of some of the main points, and instead of looking at my smug mug, here's a nice image that the authors created to outline the whole process. These authors wanted to see what happens to nanoparticles after they get into cancer, since previous theories said that nanoparticles would basically never leave. Instead, Warren Chan's lab found that if nanoparticles do get into cancer, they can leave by using lymphatic vessels, which are typically used to remove waste products. The size of the nanoparticle determines which exact vessels they use, but that doesn't matter that much. What really matters is that once the nanoparticles leave, they go back to the heart and eventually recirculate through the bloodstream. Recirculating is incredibly important as it gives the nanoparticles another chance to enter the cancer in order to try and kill it. So with the EPR effect practically dead in the water, Warren Chan's lab came up with a new theory called the active transport and retention principle. Put simply, nanoparticles are actively, not passively, brought into cancer, then they leave temporarily just before coming right back. Like any good scientist, they acknowledge that there's still lots of work to do, namely to identify specific mechanisms that bring nanoparticles into cancer, see how different types of nanoparticles interact, and to see how all of these interactions differ between cancer and healthy tissue. Hey, what's up, nerds? Editing Matt here. So after putting out my last video on that first Warren Chan paper, one of the authors, Stefan, reached out to me and offered his insight on what the ATR principle means to him and the research in the future. My take is that ATR guides the nanomedicine community by providing a more accurate framework of nanoparticle delivery to solid tumors. EPR has flaws due to assumptions of mechanisms in delivery, such as gaps and dysfunctional lymphatics. ATR improves upon EPR, but it's still incomplete. All models have limitations, including ATR. One benefit to ATR is that it is built on validated fundamental and basic science of the mechanisms of nanoparticle delivery to solid tumors. However, ATR hasn't been thoroughly tested for many clinically relevant particles, and there are still more tumor models that need to be tested. I hope to read useful criticisms of ATR that guide the next generations of scientists and clinicians. As you know, science never ends. I love we're so open and honest that it's not the be-all end-all mechanism. It can obviously be improved upon, and there's lots that we need to know. Personally, I still think it's amazing. Anytime that you can challenge what the industry standard has been for decades and have significant proof to show that it's probably an entirely different mechanism that we need to explore, definitely deserves a pat on the back. And as a nanoparticle nerd, the part that I'm most excited for in the future is seeing how this applies to different types of particles. For example, if we know that a nanoparticle made of a certain material is better at recirculating than another, that might favor us to use that particle for certain types of cancers and make better chemotherapies to hopefully save more lives. If you learned something from this video, feel free to give it a like and consider subscribing. I'd also recommend joining us on Instagram. We've got a hell of a community over there, and you get similar types of science, but in bite-sized form. If I missed anything, let me know down below. But with that, it's been a pleasure, nerds. Don't forget to tell someone you love them.